All Xilinx FPGAs have dedicated registers on the input and output pads. By using these registers, setup times for the input pads and clock to output times for the output pads can be minimized, making it easier to meet time requirements for capturing and providing data to external devices. However, using the dedicated I/O registers can have a negative effect on meeting the timing requirements within the FPGA. Their use can lengthen route delays to the internal logic. Unless the designer needs the I/O registers to meet I/O timing, Xilinx recommends that the registers be placed within the FPGA fabric. The ideal solution is that your synthesis tool, like Simplify, will automatically place registers based on the timing specifications you make. Otherwise, the following steps must be performed. Step 1. Disable global I/O register usage in your synthesis tool. This will prevent the synthesis tool from mapping these registers to the IOBs every time. This option is usually on by default. Step 2. Disable the map option to pack registers into the IOBs. Map is a part of the place and route process. It is the phase where logic is grouped into CLBs and, in our case, IOBs. Since the implementation tools have this option on by default, it may be worth evaluating your timing with this option off. Step 3. So after turning both default options off, you can now selectively move registers into the IOBs with a UCF attribute. That's the user constraints file, a simple text file for your pin assignments, pin attributes, and timing constraints. So start with your timing critical I/O pads and use the IOB equals true syntax in your UCF file or your source HDL. For more information on how to do this, refer to the Xilinx Constraints Guide. Likewise, check your synthesis vendor's documentation if you want to make these attributes with your synthesis tool or your HDL. But however you choose to make specific registers put into the IOB, try to only use the IOB registers to help meet I/O timing. Keep in mind that it is important to register all inputs and outputs to a hierarchical block when there is a possibility incremental design practices will be employed. You may recall that incremental design allows a designer to maintain the place and route solution on a module basis. The benefit is that it saves development time when you have found a result that meets your needs. So implementing the design each time now becomes implementing just the components you are not happy with. In general, these practices are popular and worthwhile, but for them to be effective in meeting system performance needs, designers have to anticipate having signals travel a significant distance across the die. To help this, we recommend registering all inputs and outputs to your most critical hierarchical blocks. Likewise, you should try to keep your I/O resources at the top level of your design. Usually this is done through direct instantiation. While inferring I/O registers is usually okay, instantiation of double data rate registers or DDR, SerDes resources, and delay resources is recommended. It's just plain easier than inferring those resources. Also keep in mind that any logic that needs to be placed in a single resource, such as a block RAM or a DSP slice, should be contained in a single hierarchical block. Any logic that needs a synthesis tool to resource share should be placed in a single hierarchical block as well. Recall that resource sharing is recommended to be turned off, but if you decide that your synthesis result with a component is best left on, then isolate that logic into one hierarchical block. Also, manually duplicate registers with a high fan-out net when it's at a hierarchical boundary. By following these guidelines, it is far less likely that your chosen design hierarchy will interfere with design optimization and performance. The idea of replicating registers that have a high fan-out net on the output still applies in Virtex-5. This allows a high fan-out signal to be moved closer to some of the many destinations where it is required. The easiest way to determine if this is part of a problem is to generate a timing report either from synthesis or after implementation, and use that to determine if you have a high fan-out net as part of the data path. If so, manual duplication is recommended. This will require you to prevent the synthesis tool from removing the extra logic, which is the default behavior of the synthesis tool. And this is done by using what is called a keep attribute. If your synthesis tool allows you to control the replication, that can also be useful. But keep in mind that replicating logic just once is rarely sufficient. Depending on how far from meeting your timing needs you will probably have to replicate that logic a few times. Once you have added registers through pipeline stages, you should also remember to allow your synthesis tool to migrate those registers where they're needed. This is done with the retiming option. Since we've been talking about registers being a premium in Virtex-5 designs, we wanted to take a second and mention some considerations about synthesis options. First of all, don't over-constrain your design. This means that you should not place timing constraints on your design that are unrealistic. As we always say, only place timing constraints that reflect what you must have. Remember that unless you are operating at worst-case operating conditions, you already have some built-in slack. Over-constraining typically makes designs bigger and increases the number of registers used, since synthesis tools tend to replicate logic to decrease fan-out on timing-critical path nets. Typically, this increases register usage by 1 to 5%. Global optimization settings don't usually solve your register usage problems, although they can generate different results. Typically, global optimization can reduce your flip-flop usage by up to 10%. However, this often forces the synthesis tool to generate extra control sets and can result in unusable flip-flops. So, feel free to try it and compare your results, but don't expect it to solve all of your problems. Finite state machine optimization can save you some flip-flops, but you'll probably have to encode the state machine yourself. This is because most finite state machine optimizations will use one-hot encoding, which uses more flip-flops in an effort to increase speed. With the Virtex-5 FPGA, the 6-input LUT means one-hot encoding is not quite as useful as it used to be with the 4-input LUT structure. I would recommend that you synthesize your finite state machine yourself by trying binary, one-hot encoding, and gray encoding. Then compare your results and see which one you like best. It is also important to determine whether your finite state machine is part of a timing critical path. Often they are. If so, you may have little choice but to use one-hot encoding. But be an engineer and evaluate the encoding yourself. Note that over time, this is something synthesis tools will learn from and will improve upon. Finally, don't use slice or LUT compression switches. While this does not consume too many extra flip-flops, in some cases latch-throughs were used, and this wastes registers. Recall that the slice does not allow you to separate the flip-flop from the LUT, so in the case of a latch-through, the LUT is used, but the flip-flop is wasted. So we don't recommend over-constraining your design. It just increases the register usage too much. We also don't recommend using slice or LUT compression switches. It can waste register resources.